Hello. Everything should be okay now. Um, let's see. Can you hear me? And do you see the desktop?
Yes.
Great. Okay, thanks. Okay, almost ready? Okay. All right. So first, um, remind you that there's the midterm exam a week from today. Okay, so it's on next Wednesday, the 31st, and I moved the review problems up to the top of the page so they're easier to find. Okay, so there's the list of topics and then a bunch of problems. Okay, so like I said several times before, solve these problems. I'm not going to give you an answer sheet, but I'll answer questions about the problems. So if you want to know if you're doing it right or wrong, or if you work with somebody else on them, that's fine. So make sure you can solve those problems, and that'd be a good preparation for the exam. Okay, and um, what we want to do today, well, there's a new programming assignment up, and then we're going to talk about that a little bit, and then we're going to finish this chapter on basic scheduling. So we'll finish chapter 7 on basic scheduling. Okay, and you have a reading assignment to start reading the next chapter. We won't get to that today. We'll start that maybe next week. Okay. Okay. So here's the homework assignment. Okay, it's got a long description. There's a lot of detail in here. So you have to the basic idea is you have to read this description really well. It's about 5 pages long. You have to read it several times and follow it very carefully. It gives you pretty detailed instructions on how to use a bunch of different functions in the Windows library. This is pretty serious Windows systems programming. So it's a real good project in that sense because it gives you a sense of pretty serious realistic Windows systems programming using a bunch of Windows functions and data structures. Okay, so here's what it is. You're going to be writing a scheduler. Let me download the zip file. You're going to write a simple little scheduler. Okay, so in this zip file, there is this file that you have to complete. That's the homework assignment. And what it has in it now is I gave you a data structure that you need. You you can use it if you want. If you don't want to use this data structure, you don't have to. If you can come up with you think a better one, that's fine with me. But I give you a data structure I think is useful, and then give you a few variables that I think are useful, and then there's a list of steps to do. One tricky step, I gave you one little tricky step here because I was afraid that that one would just be kind of confusing. It's such a weird little function call. So I put this one line of code in there, and then otherwise it's notice it's follow the directions in here. Okay. Now every one of these steps is explained in the HTML page. So this gives you an outline. This gives you a brief outline of what you need to do, and then there's the more detailed outline of what you need to do in here. Okay. So you need to read this and then follow through the steps in the code to implement what this does. Okay. Now what you're doing, there's a demo version of the program in here that you can run. Okay. So open a command window here, and if you run the demo version, okay, notice that if you just run it, it tells you that it wants command line arguments. So these are in the world of Unix, these are called usage messages. When you run a program at the command line and it wants command line arguments, it gives you a usage message telling you what you're supposed to do. So you're supposed to give this a schedule type. Okay, now well, the idea is that you want to, well, actually, I'll run it because it's probably easier to show you than it is to explain it in words. So what I want this thing to do is run a 3-second job, a 4-second job, and a 5-second job. Okay. So I want it to schedule on the CPUs a 3-second job on one CPU, a 4-second job on another CPU, and a 5-second job on another CPU. Now these jobs are this program here which we've used before. This is the program that runs on a CPU It doesn't do any IO or any blocking. It just runs on a CPU for a fixed amount of time. Okay, so we've used that program before. That's the if you run it on the command line, it says it wants a command line argument, says how many seconds to run. And if you say run for 5 seconds, it runs for exactly 5 seconds of CPU time. Remember, it runs for 5 seconds of CPU time. So remember, we did the experiments where we ran two of these on one CPU together. And if you run two of these on one CPU, and if it would take 10 seconds to run two 5-second jobs because they have to share the CPU. Okay, so if you force this command prompt to only have one CPU, remember we're using a processor affinity. So we're going to go back to talking about affinity. If you set the affinity of this prompt to one CPU, and then you run two instances of this program here, it'll take 10 seconds to run two 5-second instances. It runs for CPU time, not wall clock, what we call wall clock time. Wall clock time is the time on your watch from start to end. And people refer to it as WTC. It's wall clock time is the technical word, because everyone's used to there being a clock on the wall. So in the world of computing, especially in Linux refers to it always as wall clock time, the amount of time that you measure on a watch from start to beginning, as opposed to this CPU time. Okay. Let me check something. Okay, I just started up my little version of Linux on this machine, and I'm running a Linux program called Top, which gives you the times. See if I can remember where they are. Oh, I have to remember how to get this thing. Shows you the various times. Think what we're talking about: wall clock time, CPU time. This is the Linux command line version of Task Manager. Okay, this is Linux's command line implementation of what we think of as Task Manager on Windows. Okay, and I thought this thing would show me. Yeah, you have to remember how to read all these symbols. It shows you all the different times that you can measure. Right now, we're interested in two times: wall clock time and CPU time. There's the CPU time. Okay, let me just close that. Okay, all right. So over here, the program we're running, I wanted to run a second job, a 4-second job, and 5-second job, and it's going to do that. See, there's 3 jobs running. Okay, right. Now that didn't do any scheduling really. Now, like here, I'll run a 5-second job, a 6-second job, and a 7-second job. Now they're running simultaneously. What it's done is it's put each one of those on a different CPU. Okay. Now, actually, let me run them for a lot longer. Run a 20-second job, a 20-second job, and a 20-second job. Okay. If you notice, this one is on processor 0, strictly on processor. It's not moving around. I've told my scheduler is telling the operating system to run this one on processor 1 and run this on processor 0. This one's on processor 1, and this one's on processor 2. See, so I just allocated one job to one processor, one job to the next processor, and one job to the other. Okay, so that's the most basic thing this little program should do. If you tell it to run a 50-second job and a 50-second job and a 50-second job, it'll run this one and tell the operating system to run it on a specific CPU. So the operating system itself won't start moving it around. If I go back and open a command window here and just run this program here, we've did this before. Remember, if you run this I'll run it for a long time. Notice how it's moving around in terms of processors. See how it keeps moving around? See, if I click on this window, it stops the process. It's kind of useful to know that. If you click on the window, you actually are blocking the process. The process is paused. Then you hit enter and the process restarts. That's kind of a weird trick that you can do. It's not an obvious thing you'd be able to do that in a command prompt window. But if a program is sending output to the console window, and you just click in the console window, you pause the program. It's in the block state, waiting for you to hit enter, and then it unblocks it. That lets you like read your output. Now, notice that the operating system is moving this thing around. Remember we talked about that? It's probably trying to keep the load, the temperature. It doesn't want any CPU to overheat, for example. So it kind of spreads the work around, and it keeps moving the process around from CPU to CPU. Okay. Now over here, the way this thing is supposed to work is when I run these 50-second jobs, they don't move around. See, it stays on one CPU. They don't move around because my scheduling program has told the operating system, run this process on processor 1. It does that by doing a function call that sets the affinity of this process. So this process was set with an affinity of just one CPU, and this one was run with an affinity set of a different CPU. So the operating system obeys my instruction. So this process by my scheduler was told to run on this CPU, but it's actually the operating system that really decides where things run. So my program, the scheduling program you have to write, has to know how to tell the operating system what CPU to run each of these jobs on. Okay. Right. So that's the basic thing that it does. It runs processes on CPUs. Okay, let me let those things finish. Actually, I can just close them. I don't need to wait for them to finish. Okay. Now, right now, since I haven't done otherwise, my scheduler has access to all the CPUs. Okay. So if I bring up Task Manager, so I'm going to bring over Task Manager and go over to where we can see all our processes. There's my CMD. Well, let's see. Let's see if that is the CMD. That may not be my CMD. Oh yeah, that's the one. See, I'm homework 3. Okay. So that's the CMD that I'm running. I have to go over here and look at the command line because it could be some other CMD that I'm running on this computer. There's probably more, there may be more than one CMD, but this is the CMD that if I look over in the command line column, I can see that it's the one in my folder homework 3. Okay. And then if I look, I can check that this CMD, it's got access to all the CPUs. So what I'm going to do is I'm going to give it access to only 2 CPUs. Now it only has access to 2 CPUs. Now what should happen if I go over here and say run 4 jobs? Okay. So what your program does is it runs a 50-second job on one CPU and a 50-second job on the other CPU, and then it waits for one of them to complete. In fact, let me make this 50, 20, 30, 50. Okay. So what it's going to do, it's going to run a 50-second job on one CPU. So it only has access to 2 CPUs. Now, the command prompt has access to only 2 CPUs. So that means its children, which wouldn't be this demo program, its children only have access to the same processes that the parent does. So CMD is the parent of the demo program. So the CMD, we gave it only 2 CPUs. So the demo program has only 2 CPUs. So it's supposed to schedule a 50-second job, a 20-second job, a 30-second job, and a 50-second job. It only has 2 CPUs. So what the scheduler does is it's a non-preemptive scheduler. Like we've been talking about, it has the policy of not interrupting. So it's going to run a 50-second job on one CPU and a 20-second job on another CPU, and then wait until one of them is done. Now the 20-second job will finish first, and then it'll run the 30-second job on that CPU. Then these two add up to 50. So these two will terminate at about the same time. Then it'll run this one on one of the free CPUs. Okay. So your scheduler is really scheduling. It runs as many processes as it can on as many CPUs as it has available. Then it waits until a CPU becomes free, and then it schedules a job on that CPU. The best analogy to this is checkout lines at a grocery store, where there's a person directing shopping carts to checkout lines. This program would be the CPUs are the cashiers, These are the customers that need service. And this program is a person who directs people to a cashier. So when a cashier becomes available, it directs somebody. So people don't wait in line at the cashiers, they wait in line at the scheduler. People wait in line at the scheduler. Then when the scheduler sees a cash register empty, it directs a customer to the cash register. And then it waits to see another one empty and it directs another customer to the cash register. So that's what kind of scheduler this is. Okay. Now if I run this, now notice only processors 2 and 3 are in use. See, it only ran 2 jobs. Now, one of these is the 20-second job that's going to end first. Okay, the 20-second job ended first, and it was on processor 3. Now there's a 30-second job running on processor 3, or was it the other way around, 20 then 30? Okay, now these two will end at about the same time because 20 plus 30 is 50. So these two are going to end at about the same time, and that'll leave one process to run with 2 CPUs available. So it's hard to say which CPU will actually get the process. Okay. No, but notice that the program is really doing scheduling. It's now waiting for one of these jobs to finish. Okay, one of them finished just a second before the other one, and it got the last process. Okay, processor 2. Okay, so that in a nutshell is what this program does. It really, and then also here in this window here, it announces what it did. So it launched the 50-second job on processor with mask 4. Now mask 4 is CPU 2. See, here's the mask and here's the CPU number. So I got 2 columns here. The mask tells you, well, actually, this is the affinity mask. But see, the affinity mask has only 1 bit in it, and that affinity mask is that processor. Okay, so I kind of go back and forth between writing these things in hexadecimal and writing them in decimal. Okay, so 4 in hexadecimal is processor 2 because you have processor 0, 1, 2. So 2 is in the 4's place. Processor 0 is in the 1's place. Processor 1 is in the 2's place. Processor 2 is in the 4's place. Okay, so you have to get used to, and see, processor 3 was in the 8's place. So sometimes we're working with bit masks. Remember over here in Task Manager, when you look at the affinity, it really does look like a bit mask. You think of these as bits. This is bit 0, bit 1, bit 2. So that's the 1's place, 2's place, 4's place, 8's place, 16's place, 32's place, 64's place. And then that's how the Windows function thinks about them. There's a word that you set bit. When you set the affinity mask, you set bits in a word. If you want to turn on that like this would be the word 0011000000. Okay? And that would be in hexadecimal. That is 8 plus 4. That would be, what is that? This is A, I think it is. I think this is hexadecimal A. And in decimal, this would be the bit mask. We'll see. That's 4's place and 8's place. That's the decimal. That's the bit mask 12. So that'd be the bit mask 12 in decimal. I think it's A. No, C. It's C in hexadecimal, and it would be 0011 in binary. Okay, so you have to kind of get used to going back and forth between these. Okay, so here it said when it was launching jobs. So every time it launched a job, it put a little line here. Said so initially it launched the 50 and the 20-second job. Okay, notice that the 20-second job was on processor 8. So the 30-second job was on processor 8 because that was the one that became free first. Now, it makes sense that the next 50-second job would run on this one because it took a little bit of time. These two aren't going to add up to exactly 50 seconds of wall clock time. This is 20 seconds of CPU time and 30 seconds of CPU time. They'll add up to just a tiny bit more than 50 seconds of wall clock time. So this one probably finished first before these two. So this job ran on processor with mask 4. Okay. Now, if I want, I can give this thing there's another CPU. I give it another CPU. Now it's got 3 CPUs. Okay. If I run that command again, now it's going to run a 50-second job, a 20-second job, and a 30-second job right off the bat. and there'll be a 50-second job waiting to go on the CPU that the 20-second job is on. And let me shorten that one, make that one just a 10-second job, so you don't have to wait so long. Okay. Okay. There's 3 launched right away. Processors 2, 3, and 8. That's those are the ones I checked off. Processors 2, 3, and 8. Then one of them died and was immediately replaced by a longer job. And then if you look over here, it launched the 50-second job, 10-second job, and 30-second jobs were launched right away. And then the second job was on processor with mask 8, and that's the one that got the 50-second job because it was the one that was free first. Okay. And now notice that now the processes are dying off, but this program has to wait for them to finish. That's the last thing the scheduler does. The scheduler waits till all of the processes it launched are complete. Okay. So now these guys are going to die off one at a time. Okay. Now notice there's one left. It's almost done. And then see when it finished, then the scheduler was done. The scheduler uses a wait function. It uses the wait function to wait for CPUs to become free, and then it uses a wait function to wait till they're all done at the end. Okay. So at one point it's waiting for a free CPU. Okay, okay, here's a whole bunch of examples. I'm running 1, 2, 3, 4, 5, 6, 7 jobs on just 3 CPUs. Okay, but they're short jobs, and you can watch. See, this one over here said what it was doing. So it started off with 5, 4, and 3 on processors 4, 8, and 1. So there's the 3 processors. Okay, the 3-second job is the one that's going to finish first. So on that CPU, it launched a 2-second job. Then it was then that CPU became available next and got the 1-second job. Then that CPU became available next and got the 2-second job. And then that CPU became next and got the 3-second job. Okay. So it's a real scheduler. It's scheduling processes on CPUs. Now the operating system is doing the real scheduling, but we're interfacing to the operating system that's why the operating system lets you set affinity. It's literally there so that you can write your own scheduler. You'd be surprised how many people write schedulers on top of the operating system. There's lots of special uses for schedulers in the world of computing that are different than what the operating system wants to do for scheduling. So here's an example where we want a process to run on a single processor until it's completed. And that's not an unusual thing. So the operating system has the ability to let you tell it what to do. It has its own sense of how to schedule. Without us telling it, it would, remember we saw before earlier, it would run processors, it would move them around all over the place. The built-in Windows scheduler, same with the Linux one, it's really wants to move CPUs, it wants to move processes around from CPU to CPU. And basically it's mostly just to keep the one CPU from getting uh, overly heated up. Not that you can really overheat these modern CPUs. You'll notice that if you run one real long job on one CPU, you'll notice a fan turn on, but you're not going to overheat the CPU. But even a fan on a laptop, a fan is more battery use. So if you prevent any one CPU from heating up, you're probably going to end up using overall less electricity. Because if you can just keep the fans from turning on, that's saving electricity already on a laptop. Okay. All right. So now the things you have to worry about in this is when the program starts up, it kind of this thing sort of steps you through the steps you have to do. But for example, when the scheduler starts up, the first thing it needs to do is ask, how many CPUs am I allowed to schedule? So before it even looks at what's on the command line, it really needs to ask, how many CPUs do I have available? Like right now, this thing has 3 CPUs available to it. Okay, so it's granted 3 CPUs. Okay, okay. Um, I forgot to, I meant to put that into the demo program. I wanted the first line of output of the demo program to just be a thing that told you how many CPUs there are, because that's like a good debugging piece of information. Oh no, I'm sorry. There it is. I wasn't reading right. Yeah. See, there's the first line of output. See, when you run the scheduler, the first thing it tells you is what CPUs it's granted. So it's given that processor affinity mask. See, go back here. Okay. The affinity mask is 10C in hexadecimal. Well, C is 0011. See, those 4 bits are C in hexadecimal. Then the next 1, 2, 3, 4 bits are 0. Then the next bit is a 1, so that's, and there's no other bit set. So that's 10C in hexadecimal. So the affinity mask is 10C in hexadecimal. That gives me 3 processors. Okay. And process ID, that's the ID number of the scheduler. That's the PID that shows up in this column here. That's this number for the scheduler itself. So I'm running the scheduler. So the scheduler, it doesn't need this. This doesn't need to. This doesn't even actually need to be there. The scheduler does not need to know its process ID, but I put it in there so if you want to, it makes it sometimes easier to look it up in Task Manager. If you're trying to find this process in Task Manager, you can put the PIDs in numerical order and find somebody fast. Okay, so it's nice to have it can be hard to find things sometimes. They're in alphabetical order, so usually you can find things. The name of the scheduler is homework 3, so usually you can find it either in alphabetical order or by its process ID number. Okay, so when the program starts up, the first thing it needs to do is call a function in the operating system to find out what its affinity mask is, and then count how many bits are set in that affinity mask. The operating system is not going to tell it how many CPUs it has. The operating system figures programs know how to count. So the operating system tells you what your processor affinity mask is, and then you have to count bits in it. So you have to write a function call to the operating system, and the function call is this get affinity mask. Okay, so you call this function, and it's going to give you back what the affinity mask of the scheduler is. Okay, and then you have to write a little loop that counts bits. And there's a little bit in here about how you would do that. It's a little bit of, you have to do some bit shifting. Okay, so you need to count the number of bits in the affinity mask because that's how many CPUs you have available, and you have to keep track of which ones they are too. That's this data structure. This in the code. This data structure here is so you can keep track of how many CPUs you're given and what CPUs there are. What you're going to do is you're going to build an instance of this data structure for each of the CPUs you're allocated. So it's called a processor data. It's data about the processors. Okay. So over here, when this program was running, it was running with 3 CPUs, so it had 3 instances of this data structure. When it ran, it would create an array. You're going to create an array of this array of these structures, and you need as many of them as you have CPUs, so that you can do bookkeeping in them. So you're going to do bookkeeping in this data structure. Okay, so you need to ask what the affinity mask is, count how many CPUs are in the affinity mask, and build an array of that size of these processor data structures. Okay, and that's the first step. Okay. Then after you've found out what you're given, then you read off these numbers off the command line. Okay, so that you've just put those numbers in an array. Those are the jobs you have to schedule. Okay, now if you this could be there could be fewer or more of these than you have CPUs. Like you could have 10 CPUs and 5 jobs to run. If you have 10 CPUs and 5 jobs to run, you're just going to launch all 5 jobs right away. Or you could have 10 jobs and 5 CPUs, and so you'll launch 5 jobs right away, and you'll have 5 waiting. Okay, so the hard part is when you have more jobs than you have CPUs. Oh, when you're writing this program, it's not a long program to write, but it's got a lot of steps to it. So for example, don't write the whole program. Don't sit down and say, I'm going to keep banging on the keyboard until I have what I think is the whole program. You'll never get it that way, or you will, but it's the least efficient way to write it. The way to write a program like this is to have milestones where you say, I'm going to write a program that does this part of the assignment and get that working and completely debugged. Then add a feature to it. So for example, the first step can be to launch as many processes as you have CPUs. If you're given 3 CPUs and you're given 5 processes, just launch the first 3 processes. Don't do any waiting, in other words, or just launch the 3 processes and wait till they're complete. That would be a good first step. So if you're given, well, first step would be write the program that can write this line of output here. Write the code that can just launch it could launch homework 3, and homework 3 can say, my affinity mask is this, and my processor count is this, and my process ID is that. Get that working. Don't do anything else until you've got that line of output out correctly, and debug it. Play with the affinity mask over here and set different affinity masks and keep running the program over and over again. So you can go to the command line that you're running the program from, and you could keep changing the affinity mask over here and running the program over here and make sure you keep getting the right affinity mask and the right processor count. Test it really well. Because if this part doesn't work, nothing else you're doing is going to make sense if you've got a bug in something this simple. That's why you can't write the whole program. When you write the whole program and then go to debug it, you're debugging a gazillion things. And you can't do that. It doesn't work. So you have to have one thing done and debugged, and then you can go on to the next thing, because you have to have something firm you can work on. So you got to make sure that you're getting the processor affinity mask and the processor count correct. So that's step 1. Get that line of output. Okay. Then step 2 would be launch as many jobs from the command line as you have processor count, and just let them run, and don't worry about the other jobs. So if the processor count is 3, launch a 5, 4, and a 3-second job. And then a 5, a 4, well, a 5, 4, and a 3-second job, and don't worry about the others. Don't get that working. Get it so that it can launch however many processes there are on the command, however many processes from the command line there are CPUs for them, and then wait till they're done. Okay, launch those processes and wait for them. Okay, then when you got that, sure that it's running, and then check it by changing lots of, change the affinity mask over and over again, and make sure that you always launch the right number of jobs. Make sure they stay on their CPU. And one of the things that you have to be careful is that when you launch these things, they stay on the CPU. Look for that, because if they're not staying on the CPU, you'll see their numbers changing over. You can you can run this and you can click on there, pause it, make sure those numbers are all the same. Okay? Pause it, make sure those numbers are all the same. Okay? See, I've got these ones paused. Make sure these numbers are all the same. If you see any one of those numbers change, you've got a bug. Your program's not staying on the CPU you assigned it to. Maybe you accidentally assigned it to 2 CPUs. If you're not careful with the affinity mask, you could assign a process to 2 CPUs instead of 1 CPU. Okay, so get it, get it working confidently, where it launches however many processes there are, processors, launch those, but make sure they're staying put on their CPU and that they run for the right amount of time. So if you launch a 4-second job, it runs for 4 seconds and it stays on the CPU it was run on. So get this output here, get this output here for the number of processes as there is processor count. Okay, get that working. So that's a good basis. That's not that those 2 steps aren't that hard. Getting this output here, and then getting the initial launch of the job. So in this case, it'd be these 3 jobs here. That's the initial launch. CPUs 4, 8, and 10. Okay. Launch those initial jobs and wait for them to finish. Okay. Now the next step is the hard step. The next step is then, now what I would do is, the next step is I would say is to run one more job. after you run these 3, one of them is going to finish first. So wait for the first one to finish and launch at least one more job. Get that working. Get it so that you can run n plus 1 jobs. N being, if the processor count is 3, run 4 jobs. If the processor count is 5, run 6 jobs. So you wait till the first one finishes and you launch one more job. Get that working and make sure you debug it. Make sure it really does the right thing. And then you have a good basis to finish the problem. And after that, I can't think of any real milestones after that. Milestone 1 would be, get this outline here. Milestone 2 would be get the first n outputs. If the CPU count is n, get n of these. Okay, then do n plus 1. So that means you have to wait for the first one to finish. And that's actually, that line of code I gave you is the waiting for one process to finish. So, I mean, I gave you the line of code here for, well, actually, this is waiting for a process to finish. So this is the line of code that waits for one process to finish. So you can use that at that point. You'll need it even in the first one, because this actually waits for, what it does is it waits for one process at a time. So you'll need this line of code even for the first milestone, because when you launch the first 3 processes, I want you to, the idea should be you should wait till all 3 of them are done. So the scheduler shouldn't exit until all 3 of these are complete. This thing only waits for one process at a time. So this thing has got to return 3 times for you to wait for 3 processes. Okay. The windows, you have to read about the documentation about this. It's called wait for multiple objects. It waits on all 3 of these, and it returns when one of them completes. But then you'll have to call this thing again, waiting for the 2 that are still running, and wait for one of them to complete. Then it'll return again, and you have to call it again and wait for the one that's still running. It's a tricky little, it's the hardest part. It's actually, this first milestone already has in it one of the harder parts of the programming assignment, because what you're doing is you're waiting for 3 things, then waiting for 2 things, then waiting for 1 thing. You have to kind of count down. Wait for multiple objects can wait for any number of things, but it waits until one of them terminates. And it tells you which one terminated. You have to read the documentation. There's an explanation of it in here. It's the details are mentioned in here. What it does is it waits on a number of things, and then it gives you back a result saying which one of them finished. And it only has one of them finished at a time. And there's no ties in this. These things are microsecond timers. There are no ties at the level of microseconds. So you can say, what if 2 processes ended at the exact same time? And the answer is it doesn't happen. The operating system, from the point of view of from our point of view, even if they did really happen at the same time, this function, what we says, serializes them. So even if they really did happen at the same time, this function will think of it as one of them happened first and one of them happened second. Okay. All right. So this thing waits for multiple objects, and it tells you when one of them is completed. So if you need to wait for 3 jobs, you have to wait for 3. Then one of them completes. Then you have to wait again for 2. And you can't wait for 3 again because it'll fail. If you wait on something that's already completed, it'll fail, and you'll see that it's not working right. So you're going to be waiting on 3, then waiting on 2, and then waiting on 1. And you got to make sure you wait on the correct 2. And then you have to wait on the correct 1. So that's probably the trickiest part of the program. So in the first milestone, you'll actually work on a pretty tricky part. So that's why if you get that milestone working, it's a good foundation for finishing the assignment. And that's a debuggable milestone. Getting the program to launch n processes, where n is the CPU count, that's a debuggable step. Okay, and that's important in computer science. When you become a real programmer in a real job and you're writing real software, a lot of times that's your responsibility. You're told, write this code, and then it's up to you to figure out how to get it done. Like, what are the milestones for debugging? how can I break this down into sub steps that I can debug and I can be sure I'm getting them right. It's never going to work to write the whole thing and then just debug the whole thing. Because once you get past baby homework assignments, they're too complex. Like this is already too complex. Trying to write the whole code, trying to fill out every step in this thing and then debug it. When you think you filled out every step in this thing, it's going to be hopeless. It'll be frustrating and demoralizing. Yeah, it's doable. I mean, I shouldn't say it's impossible. It's doable, but it'll be a really bad strategy. It will just be it'll be very frustrating, very hard, very time consuming. It's essentially really a waste of time to do it that way. So the better way is get some steps working and debugged and make sure, and then save that. When you've got a milestone and it works, you save it so that you can go back. Because then when you do another milestone, you may have to change things. And then once you change things, you could break something that was working. And you need to be able to go back to the working version to say, how come it worked before, but it's broken now? That's the nature of programming. When you fix one, in software, those are called regression tests. When you add a new feature, you got to make sure all the old features still work. You got to make sure that you kind of regress back to the previous version correctly. Whenever you add a new feature, you got to make sure the old features still work because you could easily break them. So you should, when you get like a milestone working, keep it as a unit. Don't, make a copy of it, set it aside, because you may need to go back to it and look and say, why did it work here, but it's not working now in my current version? What did I change? Look for the changes and say which change could have led to a bug. Okay. So you need a sequence of these little milestones, and that's the way you can really get code written. You have version 1, version 2, version 3, then maybe version 4 is the final one. Okay. And then when you get the final one, maybe you can throw away versions 1, 2, and 3. Though a lot of times they're good to keep around if you want to go back a year later and figure out what you were doing. The milestones can actually help you document what you did. They can be real useful for educating yourself about your own code. Okay. But you need them while you're developing, and then when you're finished with the final version, you may or may not need to keep the milestone versions. Okay. All right. So that's a rough description of the assignment. Okay. The single best and most important thing is don't try to write the whole thing. I keep repeating that because I get people sending me their code and I see that they've written the whole assignment and I can see that almost none of it's correct. And they're trying to go, what do I do now? And the answer is always start over again because that's not the right way to do things. And too many people send me code like that. They try to write all of it. They've got piece of code everywhere for everything here. None of it's really correct, but debugging it's nearly impossible because there's too many intertwined steps going on. And it's just too hard to debug all of it. Yeah. So get, milestones, get part of it working. When it's worked and debugged, save it. Then go on to the next thing, add a feature, you know, get that debugged, save it, go on to the next thing until you've got all of it done. Okay. That's the best. That's the strategy of right. This is not a baby assignment. This is not a lot of code. I think my version of it's 2 or 3 pages of code. Um, it's not a lot of code. I think it turns out to be, I forget, I think it was like 200, a little over 200 lines of code. It's not a lot of code. Let's see. Right now, if you don't count this thing here, which that's just the thing that prints error messages. Right now, it's 80 lines of code. Okay, so you're going to probably double or triple that. Every one of these is just a few. Every one of these is actually just a few lines of code. So any one of these steps might be at most 4 or 5 lines of code. Some are a little bit more. Some are 1 line of code. Some of them are 5 or 6 lines of code. So maybe you'll triple or quadruple that. Okay. So yeah, if you quadruple it, it comes out to a little over 300 lines of code. I think that's about right. It's not a lot of code. A lot of code is tens of thousands of lines. You know, a lot of code is when you're responsible for tens of thousands of lines. Okay, and that's not so unusual. I mean, that's what it's not unusual for someone to write by themselves upwards of 100,000 lines of code. That's kind of pushing it. That's kind of a lot. You know, for one person to write 100,000 lines of code is kind of a lot, but there's plenty of examples of it. There's lots of famous projects on the internet where one person wrote it and it's 100,000 lines of code. It's very common for one person to maintain 10,000 or so lines of code. Okay, 10,000 lines is not considered a whole lot. Okay, and a few tens of thousands is starting to get to be medium size. Okay, so 300 lines, not that much. Now this is 300 lines of tricky code. You know, this is 300 lines of C systems code. So you get kind of a bonus for writing C systems code. So 300 lines of this is probably worth 1,000 lines of Java. Okay, this is harder code to write. So systems code in C is harder than, so if you're writing 300 lines of this stuff, it's probably pretty comparable to writing 1,000 lines in Java code. If you look at these C, when you read the documentation on these things, you get a sense that this stuff is kind of tricky. There's a lot going on. Like this is a real simple function. Get processor affinity mask. Create process is the granddaddy of all these. You know, remember, it just goes, the documentation goes on and on. And this is only a fraction of the documentation because this page doesn't document the data structures involved. Remember, there's the creation flags, there's the startup information data structure, there's all these other the process information data structure. They all have their own pages. There's pages and pages and pages and pages of information just about that one function. There's no Java function like that. There's no function in the Java library that needs 10 pages to explain it. Okay? Because there's no function in the Java library that does as much as what create process can do. Okay. Uh, so here I give you a link to like here's where you get the affinity mask, and then here's where you set the affinity mask of your child processes. When the scheduler runs these children, it has to set the affinity mask of the child so the child runs on that one CPU. So you have the scheduler will get its process affinity mask and it will set the process affinity mask of its children. Okay, so you need to look up both the get process affinity mask and the set process affinity mask functions. They're both simple. See, just two parameters. Okay? They're simple functions, but they're they're simple to use, but you have to use them carefully. So these are fortunately not hard functions. These two are pretty simple functions, but you have to think about the right way to use them. Okay, so I give you links to all the relevant documentation. Now this is a tricky one. Wait for multiple objects. Remember, I gave you the code that uses that. So I wrote the function call to that one, but you still have a lot of work to do with this one. I wrote the function call because I was afraid that if anybody messed up this function call, they would just really get stuck. Okay, so I wrote that function call, but you still have to deal with you still have to set up its parameters and make use of its return value. Okay, which is not trivial. You have to set up remember, because sometimes you're waiting for 3 jobs to finish. Sometimes you're waiting for 2 jobs to finish. Sometimes you're waiting for 1 job to finish. So you keep waiting on different numbers of things. So I wrote the function call for you, but you have to set it up. You have to have all this. Well, you have to have those two parameters. You have to have those 2 parameters set up, and you have to know what to do with this result value. So you have to set up 2 parameters and you have to deal with the return value correctly, okay? And so then you have to read this. This is not a trivial function. It's not as hard as create process, but it's one of the more complicated functions in the assignment is this wait for multiple objects, okay? All right, so I try to give you pointers to all the functions that you need. And at the bottom, there's even a little table. There's a little table of these are the functions you're going to use in Windows system in the Windows library. Okay. All right. Let me stop. Anybody got questions about this? It's a lot of information. This is being recorded, so I'm hoping that what I've just said would make a good thing to listen to when you're actually, like, you can use what I've just said in these demos as a reference also when you're writing the code, is go back and listen to what I was saying. So I tried to demo it in a pretty good way. Anybody got any question about this? I mean, you need to look at it. You need to look into it. So definitely ask questions as they come up later on. But anybody got any question right away? Use the demo version to give yourself a sense of what it should do. Okay, the demo version is real useful. Okay, the demo version, you can play around with it. You can do experiments like, what if you just run, you know, see, there's three CPUs, so it launched 4, 8, 10, 4, 8, 10, 4, 8, 10. A batch of three, a batch of three, a batch of three, because they were all 1 second jobs. So you could see how they came up in a batch of three, batch of three, a batch of three. Okay. Yeah, you can do little experiments. Eventually you want to test your program on these kinds of experiments. You want to see that your program is doing the right thing. Okay. You know, if you those went by real fast, so you could do like this. And these you can see there's three. Then you can see three, and you can see that they're running. Like that one's stuck on one CPU. See, that one's stuck on one CPU. There's the next batch of three. Okay. All right. So and then you can see the output here. 4, 8, 10, 4, 8, 100, 4, 8, 4, 100, 8, 104. Then the last two at the end, 4 and 8. Okay. They don't have to be in the right order, but you can see that it launched them in batches of three. There's three, then three. Okay. Okay. Use the demo version as a sense of what your program should do. Run experiments on, when you get a milestone, debug it. you know Try to find a way to give yourself confidence that what you've written is correct, because if you do one of those milestones and it's got a bug in it, it's just going to make the next step even harder to debug, because then you have bugs on top of bugs. That's another reason why you want to break the program down into steps, so that you can be pretty confident that your previous step is correct. Because now you might break it, when you get something working, unfortunately, when you get these milestones, it's not like the code in them is frozen. To add a feature, you may have to make changes to the code you already had working. That's why I tell you to keep it as a save it, because the milestones don't end up being code that gets frozen. In real good software design, that's actually a goal. If you're designing really good software, it should be modularized in a way that essentially the milestones, when they work, are frozen. But that means you have to design the code in a really modular way. But that way, you can debug one piece, finish it, and then forget about it. Not have to go modify it to add a feature to something else. If you find yourself having to modify a bunch of pieces of your code to add a feature, that's usually thought of as bad design. You should have it kind of where you can just, when you want to add a feature, you just work on one piece at a time. Okay, so, but this assignment's not designed that, it's not going to be designed super modularly. So if you do get a milestone written, you may have to modify a little bit of its code to get the next part written. Okay, so there is the chance that you could introduce a bug to something you already have working, and that's just, that's unavoidable, but it's still better than the wrong thing to do of writing 300 lines of code and then start debugging. Yeah, that'll just lead to grief. That's just not going to be a good strategy. Okay. Get a piece working, then get a little bit more working, then get a little bit more working. And that's a good question to ask if you have, when you start, if you want more advice on like what to do, how to structure it, you can always ask. I gave you a little bit of sense just now of what I think would be good milestones. And then, but you can, maybe you have a better idea, or you could ask if something else is a different way of structuring it. Any kind of question is fine. Okay. Any last question about this assignment? it's due after, I forgot when I made it due, April 12th. So that's 2 weeks from Monday. Okay, so that'll be 2 weeks from Monday. Okay, all right. So the exam is a week from today, and this assignment is due 2 weeks from Monday. Okay, all right. And okay, again, read this real carefully. You'll need to read it several times. It's you know, I give you in words pretty good description of what you need to do. Okay, so in words, translating words to code is not a trivial matter, but in words, I think I gave you pretty detailed instructions. Okay, that's what I was hoping to do. Yeah, I was hoping that these are good, detailed instructions in words that you have to translate into the code. Okay, all right. Now let's go ahead and go back to where we were. We were talking about scheduling. Oops, I wanted to open the. Now remember, we've talked about the our assumptions, our metrics. No, remember, I gave you. Let me see. If you download this folder, there's these notes inside the folder, and the notes kind of outline the chapter. So I thought they were, in a way, it was for my own benefit, gave me a sense of how to keep thinking about this idea. But you know, I outlined things, and you can see that I kind of outlined them in a way that's similar to what. So first there is assumptions. Here's an outline of what they, just briefly summarize the assumptions. Then after the assumptions, you have the metrics. So here's a brief outline of the metrics. Okay. Then he starts talking about algorithms. See, then the next is algorithm. So first we did first come, first serve. We talked about that in class the other day. And first come, first serve, first in, first out. It's got a couple different names. First in, first out, first come, first serve. I tend to call it first come, first serve. Okay. Okay. And remember we did it by these timelines. Remember, that's not a bar graph. I think that's kind of weird way. I mean, it looks too much like he's trying to draw a bar graph there to me, but it's a timeline, not a bar graph. Okay. So okay, like here, it's a timeline. So he's just saying that A runs from 0 to 100, then B runs from 100 to 110. Okay. So you draw these timelines, and then you use these timelines to do these calculations that we did the other day of things like average turnaround time, average response time. Okay. So you draw these timelines, and you use the algorithm to draw the timeline, and then you do a calculation. Okay. Now, remember, the key thing was that first in, first out gives you good turnaround time, gives you good average turnaround time. Okay, those were the pictures we did. The idea is that it's the idea of why do they have a short line and why do they have a quick checkout line and a regular checkout line at the grocery store? You want the people with small jobs to get attention right away. Okay, so we did pictures like that. Yeah. If you when you schedule short jobs first and before the long job, so you do shortest job first. See, this was first come, first serve. So A happened to be in line, then B, then C. So first come, first serve, put A on the CPU first, then B, then C. The average turnaround time is real high here, 110. On the other hand, if you let the short jobs go first, shortest job first, okay. Now we think of them as in line A, B, C, but they all arrived at the same time. That's our assumption. They're in line A, B, C, but they all arrived at the same time. So first come, first serve runs A, B, C. But shortest job first says, okay, of these jobs, which one's the shortest? Well, B, then C, a little bit the same length. Then run the longer one. That gives you a much better average turnaround time. And it's just common sense. It's what you do in grocery store. You have now grocery store, what they do is they set up two CPUs. essentially, they have two checkout lanes, one lane for the short jobs and one lane for the longer jobs. Here, it's the same idea, but there's only one lane. But what you're doing is you're letting the short jobs cut in line. Okay, so the idea is the shortest job first algorithm is that there's only one checkout lane, but the short jobs are allowed to cut in line and they get in line first. Okay, so the same idea. But the reason we do it is it gives us good turnaround time. Okay, his turnaround time isn't really affected that much by them. His turnaround time went from 100 to 120. He had a 20% increase in his turnaround time. But their turnaround times went from 110 down to 10 and 20. See, they see a massive increase in their turnaround times. So it's really a great idea. The long jobs see a minor decrease in their turnaround times. The short jobs see a massive increase in their turnaround times, an improvement in their turnaround times. So it's a great strategy, and that's why every grocery store in the world has adopted it. Okay, shortest job first. Okay, so it gives you, remember, it gives you good average turnaround time. And I keep emphasizing that because it's going to be real important when we get to the next chapter and we do the more complex real Windows operating system scheduler. It's going to be trying to balance turnaround time with response time. Okay, and it's going to be balancing shortest job first with something else. And shortest job's first job is to give you good turnaround time. But we're going to see it gives you bad response times. And then there's going to be something else that's going to try to make the response times good. And then the algorithm that's in the operating system is trying to blend these things. Okay. Now, if you change things a little bit and you make things arrive at different times, that was the next algorithm we had, was instead of shortest job first, it's shortest job to completion first. The idea now is that you're saying, well, not everybody arrives at the same time. So that was this picture we did here. What if not everybody arrives at the same time? Well, if you do shortest job first, you can only do the shortest job of what you have available. So for example, A arrives at time 0. He's a very long job, but he's the shortest job at time 0. There's nobody else to schedule. So you schedule A. Well, then the short job arrives and it has to wait for A to complete. So now you're back to being bad turnaround time. So the solution to that is to allow preemption. You now allow the short job to preempt the job. Now we're no longer in the realm of grocery store possibility. Grocery stores don't let somebody with a stick of gum interrupt the checking out of somebody with the two baskets. Okay, you can't interrupt a job in a grocery store. But we know about how to do context switches in operating systems. We spend a lot of time talking about context switching, so we can do interruption in an operating system. So now we allow that when a short job arrives, we can interrupt if the short job is shorter than what's left of the long job. So this is called shortest time to completion. Oh, I forgot to put it down here. I forgot to label this. This is shortest time to completion. Shortest time to completion first. Okay. The long job arrives at time 0, so it's running. Oh, oh no, this is still this is shortest job first. I forget what it was. I let's see. Did I get this right? Oh, I think I wanted this picture here. This is the one where we did it. This is one where we compared. This was an intermediate picture when we were just looking at what's wrong with shortest job first. This was looking at what's wrong with shortest job first. That if you don't interrupt, this one doesn't. This one shows that if you don't interrupt, you get bad response time. This one made B arrive a little bit before A, which is better, but B had to arrive before A. So this one doesn't. This is still shortest job first. Here's the one that does shortest job first compared to shortest time to completion first. Okay, so A arrives at time 0. A's real long. It's got 100 units of work to do, but then at time 10, B arrives. So B interrupts A. It preempts A, and B is allowed to run. Now, it's allowed to run because the amount of time that B has to work is less than what A has left. So it's whichever job has the shortest time to completion. So when B arrives, the scheduler says A has 90 units left, B has 10 units, run B. Now, when B finishes, there's no one else to work, so you go back to A. Okay, at time 30, C arrives. At that point, A has 80 units of work left, but C only needs 10 units of work time, so C's the shorter job to complete. So you go ahead and run C to completion. So then at time 40, there's only A left, so you go back to A. So then A runs for a while, then D arrives. Now this is where it gets a little bit interesting. When D arrives, D's got 50 units of work, but A's only got 40 units of work left. So A is still the shorter job. So even though D has arrived, you make D wait and you finish A, then you go to D. So that's shortest time to completion first. Okay, and you can see, yeah, when somebody arrives, we call that a scheduling point or a scheduling decision. When someone arrives, we can decide to either keep running this job or switch to the new job. And if the new job is they got the shorter time to completion, we switch to the new job. Okay. Now compare that to if it was just shortest job first. Shortest job first would say, okay, we start A. There's no interruption in shortest job first. So in shortest job first, when B arrives, he's told to wait. When C arrives, he's told to wait. Then when D arrives, he's told to wait. Then when A is finally complete, now you can do shortest job first. Well, there's B, C, and D to do. B shortest, then C, then D. Okay, right? But you have to wait until that, unfortunately, that long job that arrived first, it has to complete before you can do shortest job first. Okay, so you to make to make shortest time to completion first work, you need preemption. So that's one of our assumptions. If we go back to our list of assumptions, we're now removing one of the assumptions. Uh, one of the assumptions is, can jobs be preempted or not? Okay, with shortest job first, the answer was no, there is no preemption. With shortest time to completion first, the answer is yes, we do allow preemption. So that's one of the assumptions. So we change from not allowing preemption to allowing preemption. And so shortest time to completion first is shortest job first with preemption. Okay, so it's shortest job first with preemption. Every time a job arrives, you make a decision. This gives you good average turnaround time. Okay, this gives you good average turnaround time when processes can arrive at any time. Okay, now if all the processes arrive at the beginning of time, then shortest time to completion is the same thing as shortest job first. So if all your processes arrive at time zero, there's no distinction between these two algorithms. So this algorithm actually needs us to remove two assumptions. We're no longer assuming that everyone arrives at the same time. So that's like a real checkout lane. So we're no longer assuming that everyone arrives at the same time. And then we're also assuming that we're going to allow preemption. So we're going to change what is the distribution of job arrival times. We'll change it from they all arrive at time zero to they arrive whenever they want to. And then we're going to change what's the preemption. So shortest job first has all the arrival times are at the beginning and you cannot interrupt anyone. And shortest time to completion first is jobs can arrive whenever they want and you allow interruption. Okay. And we still don't have priority. See, there's no priorities yet. Okay. And we're still scheduling one CPU. Okay. So we're keeping we should keep track of what assumptions we're making as we go along. Okay. All right. So shortest time to completion first gives you good average turnaround time. It's basically shortest job first, but with a tweak of allowing people to arrive whenever they want and you allow preemption. Okay. So in the book, the next thing to talk about is a new metric. Okay. We now know how to deal with turnaround time. The way to deal with turnaround time is shortest time to completion first. It's a good strategy for dealing with turnaround time. But there's another thing to think about. Response time. Now, what's response time? Response time, if we look at here, response time is how long you wait from when you arrive to when you get started. Okay, so it's essentially a measure of how long do you have to wait till you feel like you got some attention. Doesn't mean that it's not a measure of when you get finished. It's simply a measure of when you get how long do you have to wait to get started. Okay, like in this thing here, B arrives and got run right away, so his response time is 0. Okay, C arrives and he gets processed right away, so his response time is 0. D arrived, but he didn't get processed till a little bit later. His response time is 40. So D's response time was 40. Okay, down here, notice that the response times were like here the response times were kind of good, at least for short jobs. Short jobs had reasonable response times. Okay, but notice that here you kind of see that the response time for D is not so great. It has to wait a long time before it gets anything done. Here the response times are even worse. In shortest job first, you have terrible response times. A's response time is 0. B arrives here and doesn't get started till way over here. C arrives here and doesn't get started till way over here. So B and C and D have terrible response times. Okay, B arrived here, C arrived here, D arrived here. They have really bad response times. So shortest time to completion first doesn't give you good response time. It gives you good turnaround time. But response time is important. The classic example people give of that is this is actually a good idea. If I switch from one tab to another, I'm actually switching from one process to another. Okay. I actually want, what if the operating system, when I switched to that process, made that process wait 2 seconds before it got a chance to respond? Then I would have a situation where when I switch tabs, I would have like a blank tab or a non-responsive tab for a second or two. And you don't see that so much anymore, but a few years ago, before CPUs were fast, you actually noticed these response times. Another example would be if you like clicked on a menu. It wasn't unusual for a couple years ago for you to click on a menu and there'd be like a 1 second pause before there was a response. There was a noticeable lag in the response. And in games, for those of you who play games, response time is one of the key ideas. Response time is from the time you press a key to when you get the response from it. Okay. Optimizing response time is different than optimizing completion times. Okay. Optimizing response time is trying to say, okay, as soon as you click on something, you get an immediate response. It doesn't mean that you finish what you're doing, but at least you see it starting right away. Okay. So shortest time to completion first doesn't in any way try to help response time. It can make you wait to start up. Okay, I'm sorry. Yeah. Yeah. This doesn't do anything good with response time. Okay. So the next algorithm tries to optimize response time. What's going to happen is the next algorithm is called round robin. It's going to do a really good job of response time and make turnaround time tank. It's going to make turnaround times become real bad again. Okay, so what we're going to do is we're going to switch to an algorithm called round robin. We'll do this next. We're going to switch to the round robin algorithm, and it's good for response time. But as we'll see, it's okay. See, shortest job first is bad for response time. Round robin's good for response time. But what we're going to see is round robin is bad for turnaround time. I think that maybe that shows up in another example. Round robin will tank the turnaround times. So we're going to get a dichotomy. Shortest job first is going to be bad for response time, good for turnaround time. Round robin is going to be good for response time, bad for turnaround time. So which one do we want? And the answer is we want both. The next chapter is going to blend these two algorithms into something that's good for response time and good for turnaround time. And that's the cleverness of a modern scheduler, is to like get your cake and eat it too by blending these two algorithms along with some other stuff and ending up with good response time and good turnaround time. Actually, it ends up being good response time and reasonable turnaround time. It doesn't end up being great turnaround time, but reasonable. Okay, so we run out of time. So what we're going to do is we're going to start talking about the round robin. Now, round robin it's actually not hard. It's real simple. It's what you're used to. You just go, if you've got three processes, you let A run for a while, B run for a while, C run for a while, then A run for a while, B. It's just the time slicing that we talked about in the last chapter. It basically just is time slicing. Let A run for a time unit, then let B run for a time unit, then run C run for a time unit, then let A run for a time unit. So it's essentially the timer that just lets you cycle through processes. That's essentially round robin. So it's not really anything new, but what the issue is that now we see that what it's really doing is giving you really good response time, but it's not giving you particularly great turnaround time. It gives everybody uniformly bad turnaround time. It gives everybody uniformly good response time and uniformly poor turnaround time. Okay, so that's where we'll pick up on Monday. We'll finish talking about round robin. And then if you look in this chapter, after round robin, they just talk about what happens if you incorporate IO, which actually doesn't change things very much. We'll see. Actually, this is the beginning of the next chapter. This actually is the beginning of the idea of the next chapter of incorporating IO and trying to blend these things together. Okay. All right. So that ends the chapter. So there's one after round robin, there's this one other idea. And then the next chapter is where we talk about the Windows operating system scheduler, the Windows Linux modern operating system schedulers, the thing called the multi-level feedback queue scheduler. Okay. All right. Any question? Okay. So yeah, if you got questions about the review problems, please ask. Okay. So if you end up with any questions about review problems, please ask. If you have questions about the new program assignment, if you want to start working on it, you can ask about those too. And then on Monday, we'll finish talking about round robin. Okay. All right. So I'll go ahead and quit here. Have a nice weekend. Bye-bye.